So, as I said, I'm a principal researcher at Microsoft Azure Quantum, and what I'm going to be presenting today is kind of a few of the highlights of what we've been working on and what we've presented this past year. It by no means covers everything that we've been working on, just the highlights. And I used to be in academia, but I'm not anymore, and so it's important to kind of like understand, what drives a company like Microsoft to work on quantum computation. Just as a reminder, we've been at it for quite a while, for 25 years, and we pursue this dream because there are like real globally important problems that we think we can tackle with a fully functioning quantum computer. We're convinced that a functioning, fault-tolerant, large enough, fast enough, small enough quantum computer can solve problems having to do with chemistry, with material sciences, and thereby solving problems that have to do with carbon capture, with increasing the efficiency of fertilizers with better batteries. And that's the kind of reason why we're pursuing it. And so what I'm going to be presenting is kind of our way of thinking that really starts with what is that we want, and then what do we need to get what we want. We do not approach it as what do we have, what can we do with it. We kind of take a different approach. And so we've all seen this plot where there is a increase in resources that classical computing takes as the problem size increases, and that the growth of this resource under quantum computation grows less strong. So here we see what should it be, quadratic versus linear, and this resource that you can care about when you perform computation can be cost, it can be energy, but here I focus on time. It has to be time that we want to perform a computation faster than a classical computer can do, and that we want to solve something that we care about in a time frame that makes sense. And so if it's an important enough computation, a few weeks is okay, but a few hundred years is not okay. So that's kind of our first kind of constant. It's going to be time, and it's going to be, at most, a month maybe that we want to perform our computation. And then we have to ask ourselves, well, how good are we at the moment at solving computational problems in chemistry, in material sciences? And so then you take a look at something, really kind of like, I wouldn't say state of the art, because then my colleague said NVIDIA gets upset, but let's take this example, right? Let's take this example of a GPU chip, that is available now. And let's put that opposite to a quantum chip. And at the moment, I'm going to talk about seconds, and I'm going to talk about logical operations. So the qubits are logical qubits, fault-tolerant ones. The clock speeds are in terms of like logical operations. And then so we have the hard numbers on the left. Billions of transistors, less than nanosecond cycle time, these kinds of numbers. And then when you think about, okay, what is, a very ambitious but conceivably, achievable quantum device, well, it would be something that has like tens of thousands of logical qubits and cycle times that run in microseconds. And so these things work in parallel, right? So you've got, order 10 to the 5 more transistors classically, and order 10 to the 4, 10 to the 5 faster cycle times. And things happen in parallel. So then when you kind of like simply said, it's a little bit more advanced than that, but simply said, when you multiply the two, you get a difference in like operations per second between quantum and classical of 10 to the 9, maybe even 10 to the 10. And that is a huge, huge disadvantage for a quantum computer. It will catch up with the classical device, but if it only catches up like 100 years from now, then we're talking an academic exercise, but it's not practical. And so you have to kind of like think about, okay, so where can we make that crossover point work? And so here is an example of a calculation in chemistry having to do with carbon capture that we've pursued at Microsoft, where we look at, okay, so where does this crossover point occur for these, ambitious but realistic parameters, and when does that crossover point occur? In 2014, it looked hopeless. In 2017, we noticed that we could do much better. And more recently, we kind of come up with like, okay, here is a setting where a quantum device outperforms the classical device in 1 month's time of computation. And so you see here, that it takes, research, it takes, development to kind of get to an answer like that. It's not instant. It's not like you pick a paper from the shelf and you have this answer. This is hard but important work. And so when you look at that kind of situation, okay, so how does that look like in more detail when you have like when you really figure out all the details, all the assumptions, like how does that look like? So here's a different calculation, but of similar in flavor. It's again in chemistry, we're assuming error rates of 10 to the minus 6. Now, error rates is always a little bit tricky because that's like a monster with several heads. You've got like Clifford error gates, non-Clifford error gates, measurement error rates. So, but the 10 to the minus 6 is like the smallest of these error rates. You assume some kind of nanosecond, hundreds of nanoseconds clock speed, and then you crank the numbers, or better yet, you roll up the sleeves and you do the calculation. And so then you kind of have, in this example, it's where the quantum computation takes like 2 weeks. The number of physical qubits is 1.5 million. The number of logical qubits is close to 3,000. This kind of ratio is typical. You see this all over the literature. This should not surprise you. You see 10 to the 11th kind of logical time steps, and the number of T states, the magic states that are needed to implement the fault tolerance, also 10 to the 11. And because you've got so many time steps and because you've got so many qubits, the individual logical error rates has to be like really small, 10 to the minus 17. And we're not going to build a physical device with an error rate of 10 to the minus 17. So error correction plays a crucial role. That's why these numbers are so big. And but when all is said and done, you vastly outperform a GPU trying to do the same computation. So you look at this kind of calculation and you say, oof, that's a lot. But you look at other applications, material sciences, we think it will take more like tens of millions of physical qubits. A scientific understanding, verification of modeling, that can start at tens of thousands of qubits. But as it stands now, to the best of our understanding, and the field has been working on this for quite a while, it's going to take at least 1 million qubits physical qubits to perform the kind of computation that has like impact that is of global importance. But I want to go back to how we get to these numbers. Well, first of all, I want to remind people that 1 million bits is really not that much if you just describe it as 128 kilobytes. I mean, that's a simple attachment to your computer, to your emails. So 1 million, it sounds so much, but classically speaking, it's not all that much. But obviously, experimentally nowadays, it is a lot. But what we saw was that 10 years ago, less than 10 years ago, we didn't even think that 1 million was enough. We thought it was just completely undoable, that it was a pipe dream. It's unrealistic. And so this progress that you see here on the left, where 1 billion becomes 100 and 100 becomes a month, that's not hardware progress. That's also not progress in terms of like inventing completely new algorithms, like going from exponential to polynomial. It's the kind of thing that happens in algorithmic development all the time, that algorithms get improved over and over and over again. When you look at machine learning, when you look at optimization, linear programming, you will see that these beautiful historical analyses of like where were the algorithms in the 70s and what was the hardware in the 70s and where are the algorithms now and where's the hardware now. And in many cases, you will see that the algorithmic improvements have been more crucial than the hardware improvements. You need both, but I really want to kind of stress that the room for improvement in getting better and better algorithms in a way that goes beyond pen and paper analysis is significant. Historically, this happens all the time. Algorithms always get better, and the magnitude with which they sometimes become better is astonishing. And so that kind of like refinement, that kind of improvement of the algorithm, thereby reducing the resources that we need, is a process that is done in a way in practice. You have an idea, you implement it, you see how it works, you benchmark it against another algorithm, you refine, you do this over and over again. And that, of course, is perfectly viable and perfectly realistic when you think about classical computers, because you just run these benchmarks and off you go. You get immediate feedback if you're on the right track with your heuristics, with your ideas. So what we want and what we need while the hardware is improving is a way of kickstarting this process for quantum algorithms, a way of designing quantum algorithms and then seeing now how well they do. Is there a way of reducing the number of qubits? Is there a way of reducing the circuit depth that really kind of significantly reduces the required quantum resources? And so this, of course, is not like I'm not the first to tell this, and people have been working on this. But this was like this is a lot of work. This is like 2014, 17, like 3 years. You want to accelerate that process. You want to automate that. You want to be in the same position that people in classical computing are, where they can do this like almost instantaneously. And so internally, we have developed this tool, and last November we made it available to the public, is our Azure Quantum Resource Estimator. And it's a functionality that we provide for free on Azure Quantum, where you can take your code, run it through the estimator, and it will tell you, well, with these and these assumptions, that's how many qubits you need, that's the clock speed that you're going to need, this is the kind of t-states that you need. And we make this available because we believe that having such a tool will benefit the whole field, and it is a crucial part of going forward in our field. So this was announced in November. It was, of course, in a preview with some of our partners. Classic already mentioned it, and tomorrow there will be a presentation by Alice and Bob, who've also been working with our resource estimator. So for everybody else who was not part of that, who has not looked at it, and I apologize, there's a lot of data, and therefore it doesn't show all that well on this slide. But how it works is that you get into your account, you start up your notebook, you go programming, and then you call the resource estimator as a backend. So you're not saying like, I'm going to run my algorithm on a simulator or on some hardware. You say, I'm going to run it on an estimator. So it acts as a backend. And you provide your code, but also you can provide the parameters. You can provide like, okay, these are the error rates that I want to work with. This is the kind of fault-tolerant error correction scheme that I use, be it surface code, be it Floquet codes. You can specify all these parameters because you have a certain type of hardware in mind, for example, with certain clock speeds and so forth. And then it will tell you, these are the numbers, these are the physical qubits that you're going to need, and so forth. And you can play with those numbers and see how it changes. So it turns out that as we've been kind of talking about this, that not only is this a great research tool, it's also a great tool for exploration. Like to understand really where these numbers come from, like why, it works out the way it does. It forces you to understand the full stack. It's a beautiful educational tool to kind of understand like what is involved of going from the solution that you're solving, the solution that you're computing, and the hardware needed. So it has like this side benefit of being, both for innovation and for exploration. And the way it works, like I said, is that you can bring your own application program, or you can use some libraries that we have available, be it in Q#, be it in Qiskit. You can bring your own compiler, but we also have standard compilers available. On the right, you can use visualization tool. You can set up your qubit parameters to the model that you feel you're interested in. You can specify your error correction scheme. And then so from the right, you've got the physics. From the left, you've got the computer science. And in the middle, to make it all work, we use QIR, the quantum intermediate representation. And so that's a crucial component to be able to have this kind of flexibility. And we've been a proud member of the QIR Alliance, and we're really happy to see it kind of in action in this context. There's a QR and a link that will give you more information about how you can start using this resource estimator after this talk. So we have these numbers, and then the question is, well, are we living in La La Land, or is this something that we can hope for or can strive for on the hardware side? And so when you see those numbers, the clock speeds, the sizes, the number of gates, you realize that they're like you have to hit like 3 bullseyes. Your system has to be controlled. It has to be you have to operate in parallel, and the overall the worst kind of error rate has to be 1 in 1,000 or better. It has to be fast enough. You want to kind of have your elementary gates in less than a microsecond, 10 to the -6. And you want it to be small enough because all these qubits, you want it to fit on something that you can fit in a closet. So you want it to be tens of microns, so 10 to the -5 diameter. So these are tough requirements. These are requirements that are especially tough to have them all 3 for a kind of physical qubit model. And at Microsoft, on the hardware side, we're pursuing a vision, a goal of building a quantum computer using topological qubits. And last March, we were very happy to be able to announce that we reached a crucial milestone in this goal of building topological quantum information. Some of you might not have heard it. It might be because the title of the article is a little bit obscure if you're not in the know. But what's important is that what we were announced and what we published on the archive is a device where that passes the topological gap protocol, meaning that we showed that it is in what's called the topological phase of matter, and these topological phase of matter properties makes it inherently robust against error. It's not fault tolerant, but it gives you the kind of reliability that you're after. It also gives you the kind of size that we're after. So how does this look like? You've got a nanowire. You've got these 3 connectors. This is a 3T gate, and then you've got these quasi-particles, Majoranas, to the left and to the right, and they are. Their state, they can be in one of 2 states, and that state is protected by an energy gap. That's why we call it the topo gap proof. And so this was something that we've been pursuing for a long time. I'm very proud that we have achieved it. And this does not yet make a qubit. You need a few of them to make a qubit that you can control, measure, and have all the properties that you want a qubit to be. So that's next in line for us. We have made this, the data, all the raw data, all the calculations, we made it available to the public. This was also, we had a busy November, let's say, put it that way. Again, by going to Azure Quantum, you can see the raw data, you can see the notebooks that show how we derived the graphs in the article and much more. And again, you're invited to explore this all this data. And so the resource estimator is on Azure Quantum. The data of the topological gap protocol is on Azure Quantum. There's much more on Azure Quantum. And it's really because we believe, and again, we've got experience, is that when you want to pursue performance, you have to do it in an integrated manner. You have to build a system, it has to fit together. You have to have your classical resources and your quantum resources together. And that's why we're developing the Azure Quantum Platform, where it goes all the way from hardware access to writing your high-level quantum code. If I picked your interest, this January we start off a webinar series. This was already announced by Matthias Sukken yesterday. In January, Christoph Swoor will speak. In February, we'll have a talk by Chetan Nayak. In April, Matthias Treuer will speak. These are half-hour webinars that you are free to attend. And again, you can sign up using the QR provided there. And with that, I'll thank you, and I'll be happy to take any questions if there's time for that. Yes.
Talking about resource estimation.
Yes.
So in the morning, we heard a talk that in 9 years, there is 50% chance that RSA 2048 is going to be broken using source algorithm.
Mm-hmm.
And so you can run it through your resource estimation tool also to find the requirements to break the RSA 2048.
Yeah.
Can you comment on that, or whether it is feasible? And I have a second question, completely different.
Okay, let's do the first question first. So the resource estimator does not predict the future. So I cannot comment on the years and percentages. But you can definitely, and one of the demo notebooks that is available in our resource estimator, we've got a number of notebooks. That one does address the factoring algorithm. And so it, again, hits a number like 1 million plus physical qubits with what we consider reasonable assumptions about error rates, layout, and all that kind of stuff. Yeah. So it's a statement about what the resource estimator will tell you is that the number of qubits there will be, physical qubits will be like 1 million.
Yeah. And you can compare that with various companies' roadmaps about how many qubits they're going to produce in 2030. And if there is a difference, then maybe it's not feasible.
Yes. Yep.
Okay. Yep. And the second thing is that in your estimation, you assumed 100 nanosecond gate speeds. Does that preclude some of the platforms like ion qubits or neutral atom qubits, which are slower?
Yes, I mean, it does force you to kind of take a look at, like I said, okay, what platform is going to provide those three topics? And yes, but also like you want to have the number of qubits, and that's also kind of an important thing. So I don't want to single out one parameter as being more important than the other one. We have to have all three of them.
Great talk. I particularly appreciated your comment about the evolution of protocols of sort of algorithms, but to kind of red team you a little bit, sort of the same thing will happen in classical algorithms, for example, for like chemical analysis. So can you comment? So how do we how's quantum going to get ahead of the race in many ways?
Unfortunately, I couldn't quite understand the question. How can quantum?
So you were pointing out, for example, for a specific algorithm, that the innovation in the quantum algorithms created an advantage and reduced from 1 billion year to 1 month.
Yeah. Yes.
I mean, the same thing is going to happen in the classical algorithms. And so, how do you overcome sort of
Yeah, let's hope not, right? That the I mean, you see the improvement, right? From what was it, 1 million, 1 billion to 100 years. That's like low-hanging fruit. Like the initial improvements will be much more significant than subsequent improvements. Like something like Moore's law doesn't apply there, and so I think that it's reasonable to say that the amount of algorithmic improvements that we can expect from the quantum realm, which is much, much younger, that the improvements will be much better, bigger than the improvements that we're going to achieve classically.